like that a bit more. Now the walls here are just shown as single lines, but if we were doing a working drawing, we would want to show something of the construction of these walls,
Yes.
say the brickwork and the blockwork. Can we do that?
Yes, by all means. What I'll do is I'll shrink that down so that I can work a bit more to it. So what
Give us a bit more space around
that's
the
right.
edge to put the
So
walls in.
what I'm going to do is I'm shrinking that screen
Mhm.
down into this box which I'm creating here.
Right.
So I'm really windowing out
Right.
of the system. And what I'm going to do is swap menus over, which allows me to put in walling symbols. These are all
Other menus.
other
you've got.
menus which we
Yes,
use.
with other symbols and other functions. So what symbol is this?
This is a corner unit. We're going to put on the corners first of all on the screen, and then we're going to put in the walls afterwards. So I want to be able to use the joystick to be able to position it,
Mhm.
and all I do is simply point to where I want that corner to go, like so. Now that corner comes in as in one orientation as it was created.
Yes.
And what I want to do is now flip that
Twist it
round like so. So let me just, there you can see that it's coming round now. Okay,
Right.
and that has pulled that symbol in.
Right.
Now what we can do is do exactly the same for the other symbols.
For the other corners, right.
So let's pull in another corner in there,
Right.
and again, twist it round.
Right. Now, in fact, this is, of course, going to be a continuous brick wall, but you're just using symbols to draw the corner bit.
That's right.
Left corner, right.
So there are our symbols, and as I say, what we now need to do is pull in another symbol which is going to stretch walls from one corner unit to another corner unit.
Right.
So again, selecting it from the menu, and all I need to do now is point to one of the corners,
Mhm.
like so, and it snaps to that symbol,
Right.
and then the other side of the symbol. And
Right.
again, it will put that
So
symbol
this
in
is a
for
kind
me.
of elastic symbol whose length is defined by those 2 points, those
That-
two
that's-
cursor
that's right.
positions to make a continuous run of brick wall.
There it is.
Right. Now, Peter, you've filled in the windows and the doors with brick wall. Can we get those back somehow?
That's right. The actual openings are a symbol again. So
Right.
we can select the symbol from the menu, and this allows us to point to the wall that we want the symbol to go into. And there are several ways of putting in the window. We could issue a command a certain distance from there. So if I said 600, it would move along there and put the symbol in for me.
Yeah.
I'm going to use the actual J option, which allows me just literally to sketch in where I want it to go. It erases where it was and then redraws it in.
Right.
So again, I can do that one.
And it closes the ends of the walls and puts in the top view of the
That's
sill
right.
and whatever, yes.
Which is in effect sort of retrimming.
Yes.
So I've got a window over here. Again, J option, and place it in there. And really we need to do doors
The
now.
doors as well.
So again, select it from the,
It's another symbol for
Symbol.
the door opening, yes.
select the wall, J option again, and again point to the jamb where I want it to go in. Now these door openings and the window openings could be variable as well.
Sure.
These have been previously defined.
Right. In this case, Peter, these symbols carry on them already, this conventional hatching to signify brickwork and blockwork. But supposing we wanted to hatch some other area, we wanted to define an area and put in hatching, can you show us how to do that?
Yes, the way we define the hatch is actually to be able to, again, move to where you want to start creating, and, well, you just type in move J. So let's hatch this chimney here.
Right.
So I'm moving to one of those corners. I'm going to set the tolerance of 150. Move J. So again, it snaps onto it for me. I then issue a command called face and specify a hatch to it. So if I say face hatch equals, well, if we're going to use block work, hatch pattern 2 is the block work.
Right. So
And
predefined pattern.
that's right. And again, it's prompting us for a vector description, which, as we did earlier on with the lines, we can issue either the Q or actually type in the vectors that we want. I'm going to use the Q option, which allows me, again, just to sketch.
To go round the vertices of this face.
And R to return me to the start.
And there's the hatch.
There it is.
Right.
Okay.
Now, one of the few things missing from this drawing to turn it into a completed working drawing is some dimensioning. Can you show us how to add dimensions to it?
Right, well, what again I'll do is I'll shrink that down so that we can put some dimensions onto the left-hand side of the drawing.
Okay.
So again, I'm re-specifying the size of the screen, and that will get blown down into a smaller area. Now, there are many ways of actually putting in dimensions. We can lock onto certain corners, like those symbols, for instance. Each one of those symbols has what we call a node point, and we can actually lock onto them. So I could literally point to each one of those symbols and it would put in those dimensions. The way I'm going to put the dimensions on here is actually using the joystick and literally just using the tolerance to work to. So...
Right, so the machine will know the positions that you're referring to.
That's right. So I'm selecting from the screen menu, dimension by puck, and all I need to do now is simply say start dimension, let's say there, end dimension.
Right.
And it calculates that distance and puts in the text accordingly.
Puts the size on.
So it is start, end.
Yes. Because the description in the machine is to full size, these calculations can be made directly.
That's right. And we can do a total run all the way down there.
Lovely.
And because it's as a, you know that run equals the total run as well.
Right.
What normally happens in a design practice is certain people are given certain tasks to do, and with our system we split the layers down into, say, just the external walls as an elemental layer. The windows are again another elemental layer. The furniture is another elemental layer. Any pipe work is another elemental layer.
So all those sets of data would be stored separately, and then you could call them up and combine them into different drawings, either on the screen or plot them together.
Actually on the drawing, yes. So you have a mix and match so that you can get your communications to your contractor a lot better.
Can you show us, for example, how we would put some radiators in and some pipe work?
Well, what we have to do again is just swap these menus over, because we have a menu specifically for radiators, and this is it here. So again, we just position it onto the pad and issue the command to position it. So
again.
if I just type in do D2 start C, again I will be offered all the varying applications. We want to this time do mechanical symbol manipulation. And again, it asks me to position the bottom left-hand corner, right-hand corner, and top left-hand corner. So that is now active. Again, it just wants to know a particular level on the screen to start working at. What we now need to do is start putting in the radiators, and what we can do is select the item from this symbol library on the pad. You can see on the pad here a sort of block of symbols. And we're literally just picking items from there.
In the way we did before, yes?
Yeah. So, picking a radiator. It's asking me the length of the radiator. So let's type in 1800 millimeters. And it's now asking me for the angle, because again, once you create a symbol, it comes in a certain way. So what it needs to do is know the angle of it. And if I type in 270, we can put a radiator in there. Now, it is centrally justified again.
Right.
And in goes that
There
radiator.
Yes.
Okay. I can then re-change the angle, and let's go to 90 degrees.
Right. So this is the orientation of the symbol.
That's
The
right.
drawing.
And put another one there.
Mm-hmm.
And that is how you tend to put in those radiators. The way we can put pipework on first is actually to use a drawing routine, and on this menu, on the pad, you can see sort of creation items in the yellow. And what I want to do is create orthogonal lines. We have an orthogonal and also a non-orthogonal method of creating lines. So I want orthogonal lines, and I want to generate them continuously, and I want parallel lines. So let's have an offset of 200 millimeters so that we can generate a route of pipework.
Right, so these are going to be the supply and return of
That's right.
to the radiators.
We can actually have up to 10 parallel lines at any one time. I now want to move to a particular location, so let's start up here. I can then issue the J command again, and whenever I go, let's go down to there, it is going to generate me a line. I can then go to there, and as I've given it second angle, it has put in the first parallel line and also mitered
The corners,
corner
right.
automatically. So again, I could come up to here to issue that line.
Right.
I can then come out of that, again the last line will be put in. So what I want to do is connect a line. Let me just zoom in slightly into this
Right,
area
to
so
see
that we
this.
can actually see it
Seems a bit
happening.
closer. Right, we can get a much clearer picture now of some of this detail, the hatching and the blockwork. Here's the radiator, yes.
So I'm selecting from the menu now to be able to create a perpendicular line to the radiator. So it first of all asks me to select the actual line and then the radiator that I want it to connect to. And what happens then is it drops the line from the radiator to the actual line itself.
Right.
So I could select this line now and then this radiator. So again, it will drop that line for me.
Fine.
That's totally automatic.
Right. Supposing we wanted a valve on this supply pipe here, what about that?
Well, again, that is a symbol. So what we need to do is select the symbol from the menu. We have an isolating valve. And all we need to do here is select the line that we want the valve to go into. So if I select that, you can see that it has gone in. Now, a point to note here is when the symbol goes in, it re-trims the line, so that line is not going all the way through.
All the way through the symbol, right.
Okay, so if you watch on this bottom line on the screen, you'll see it happening. It's very quick, but you might just be able to see it.
Right.
So you still have the symbol coming in, and then the line's going in. We could, for instance, use a three-way valve in this situation. So if I select the three-way valve from the menu, again it asks me to identify where I want, in this case here. It will bring in the symbol, and it will first of all really check to see whether it is in the right orientation, and it will automatically re-justify it.
And finally, Peter, what about some directions of flow on those pipes there?
Right, the direction of flow is again a symbol, and again all you do is simply point to where you want the symbol to go, and it will put that arrow in.
Lovely. Thank you very much, Peter.
Having seen the facilities that the system offers, we went to Preston, the home base of BDP Computer Services, to look at how it tackles a real problem, the design of a technical college.
In this particular case, the site was very restricted, which determined to a large extent the general form that the building would take. We thought that the economy of the whole job required a repetitive and simple construction element, and all of these factors added together made the use of CAD a good tool, first of all, to demonstrate to the client how his building would roughly block up, so that you get a demonstration on here of how you turn the corner with the building. Subsequently, we were able to design in rather more detail the turning of the corner, the positioning of the staircase, which is in this tower, and the positioning of windows. And we could see that concept from more than one viewpoint. Again, this was essential because it was not only a matter of the design of the building per se, but fitting it into adjoining older school premises and domestic accommodation, so that the client could see, and we could see as the design developed, how that fitting in would take place.
Like many drafting systems, Acropolis offers the facility to organise drawings into a series of layers. These can be thought of as a number of transparent sheets which are superimposed to make up the complete drawing. Each layer can be selectively edited without affecting other layers. Architectural drawings, then, are often made up of quite simple constructions. But engineering drawings, like this exploded view of a gearbox and shaft, require more complex geometric operations. David Brown Gear Industries in Huddersfield manufacture gears for process plant, conveyor belts, even tanks and aircraft. The size of the boxes and the gear shafts inside them being manufactured here will vary enormously depending on their final use. But essentially, each unit will be made up of the same major components: the box, oil seal covers and shaft. In the case of the shafts, their geometric similarity allows them to be treated as a family of parts. Only 20% of the gearboxes that David Brown supplies are standard catalogue items. 3 years ago, they purchased a Camex CAD system to help them produce drawings for these and the remaining 80% of their output, which are client specials. So how would this drawing for a new gearbox cover be constructed? CAD supervisor Alan Siswick.
All right, well, we'll start off doing this cover drawing in terms of using the system. First of all, we'll set off some construction lines for reference, put on a vertical and a horizontal. We can then take some offset lines from there to give us the width. Having put the offset lines in that way, we can come back and put some more horizontal ones in.
The offset construction lines will be used to build up the outline of the cover's profile. Alan selects a small area that he'd like to work on in more detail. He identifies with a box the area he wants to work on and adds in further offset construction lines which identify the exact profile of the cover's section. When he's happy that these are correct, he gets the system to draw a continuous line over those parts of the construction lines which correspond to the outline of the cover. Finally, he adds in a small fillet radius to complete the outline. The construction lines are erased to reveal the outline of the section. But this is only half of the section. Because the gearbox cover Alan is drawing is bilaterally symmetrical, the computer can perform a reflection transformation and mirror the other half below. To do this, the completed outline to be copied is isolated, reduced, and the construction lines replaced. Alan then locates the center line, which tells the system where to mirror the outline he's drawn. He then puts the system into copy mode, and the other half of the image appears below. This completed, he once again enlarges the image to a more convenient scale. The two identical halves are then joined up with straight lines to represent the completed section. Using a facility which allows features to be identified selectively, Alan isolates with the box those parts of the drawing which he would like cross-hatched. He must tell the system the angle of hatching required and the separation of the lines. The temporarily erased lines are then replaced, and on command the identified areas are hatched. Returning to the smaller scale, the geometry of the original temporary construction lines will then enable him to set out the circular front view of the cover. New construction lines identify the center point in this view. The diameters of the various circles required are specified to complete the drawing. The system generates concentric circles which define the outlines of the cover in front view. Using the system's rotate feature, 4 fixing holes are added. A chain line circumference and 45-degree lines from the cover's center define the center points of these holes. Construction lines are finally removed. A drawing frame, stored as a standard object, is added, and in the boxes provided are added the drawing title, number, scale and date. The cover drawing is now moved up in the frame to allow room for dimensioning. The system is asked to measure particular points on the drawing. Because dimensional information is always put into the drafting system as actual sizes, that is effectively at a scale of 1:1, the system can calculate true dimensions from the coordinate information directly and add the dimensional annotation automatically to BS308. So it's taken Alan about 6.5 minutes to create this drawing. But let's have another look at the gear shafts. As we saw earlier, these are composed of a series of elements with different diameters, which differ according to the function they'll have to perform. But all gear shafts retain a geometric similarity. The shaft we're looking at here has 5 elements. Using a particularly powerful CAD feature, the ability to define families of related shapes or symbols parametrically, exact details and dimensions of each element of the shaft can be typed into the keyboard in response to a series of questions. With this parameterized definition, the software can create a fully detailed drawing of the shaft automatically. No work with the puck or menu pad is required. So how do we create a drawing of a shaft using this parametric software?
The first screen that we get here is just header information that would go on the drawing. So the first thing that we would put in there is the user initials. And we're just drawing a plain shaft in this instance, so we don't really need to put this gear center distance in. I'll specify the size of the unit as a H2 200. The H2 there is the particular type of gearbox that we're drawing the part for. There's going to be no ratio. The shaft location is the position in the gearbox. This is the first shaft. We can provide, the program will provide us with extra information at the back of each prompt because the questions are a little bit short. On this particular example, these are the types of basic shafts that we can draw using this program. What we're going to do is a plain shaft, which is a type B. We'll put the title in. And in this case, we'll put a drawing number in, 23. There's no gear particular specified there because we haven't got the gears on this shaft. The material is 655M13. Heat treatment code, we won't heat treat this, there's no gear teeth on it. As this is a new drawing, the issue number will be 1, which the default is supplying, the program is supplying as a default. So that's all the information on the header, which is now correct. What we're doing now is describing each segment on the shaft. From the shaft that we saw earlier, you could consider each section to be a small cylinder made up along the shaft. So we want a plane segment in this instance. The reference face is the position to which the dimensions are referenced, which we won't want on this one. The track is a description of what sits on this particular part. And in this case, we've got a bearing. There'll be no thread, no tapped end. If we put in the shaft diameter as being 100 nominal, we could at this point put in an ISO tolerance on that dimension, which we can skip, or we could put in specific tolerances. But because we've told it it's a bearing, the program will put a default tolerance in for the bearing. The length we can make 65. There won't be a radius at the first end of the shaft. At the second end, it would default to a fairly generous radius. What we need there, because of the bearing, is a tighter radius than that. So I'll put a 2 in there, with no chamfer. There'll be no keyways, and we don't need the lead on there. So as such, there's sufficient information there to define the first cylinder. So we go through now onto the second one. This is going to be a plain location diameter. Put this, we don't need to specify.
So information for each of the 5 elements of the shaft in turn is requested by the software and punched in on the keyboard. The system asks for very detailed information because engineering parts must be manufactured to a high standard of accuracy, and details of all dimensions, finishes and tolerances must appear on the finished drawing. The whole process takes about 5 minutes.
That's completed the process. So all we need to know now is run a separate extension to that program which will generate the graphics.
A detailed drawing of the shaft just specified appears on the screen. Where a keyway occurs on an element, a cross-section is drawn below. Notes, annotations and dimensions are added automatically. But what would happen if this drawing needed a small modification?
We're going to modify this drawing that we've got on the screen now by extending the extension on the right-hand side by 20 millimeters. First of all, I need to tell the system all the geometry that we need to move over. It takes a moment for the system to collect all that data together, and then we can tell it how we want to modify it. In this case, we're going to stretch it, and I can define the axis along which we want to stretch it. In this case, 20 millimeters. The system will then modify all the geometry that's affected and redraw it.
The system can then be instructed to plot the drawing, either on a pen plotter, which is very accurate, but can take some time if the drawing contains a lot of detail, or on an electrostatic plotter. With this method, the drawing is composed not of lines, but of minute dots. All drawings are plotted at the same speed, whatever their level of detail. So what other benefits can CAD offer David Brown gears? At present, the NC machines which cut the parts are programmed by hand from the geometrical information in the 2D drawings. But in principle, a 3D description produced by the system could be fed directly to the NC machines. David Brown planned to make this link in the near future.